Hello, this is the second recording covering the anodized parts case study in Chapter 6. And in this particular video, we're going to begin discussing how one goes about evaluating a continuous measurement system. So in Six Sigma, we sometimes call this Continuous MSA. Okay. And I just point out, in general, even apart from Six Sigma, measurements are just overlooked in terms of their importance. Many process problems, many quality problems, people assume it's part of some process or product produced. And there are many cases where it turns out the problem was actually in the measurements, not actually in the process or product itself. And what this can do, this can lead to a lot of wasted effort and time trying to fix a process or product where there's actually nothing wrong with it. What was wrong were the measurements being used, and they were being accepted by, say, whoever the researchers or engineers or continuous improvement staff who use them just assumed they were capable. So in this section, we're going to talk about some of the approaches to evaluating continuous measurement systems. This is not in any way intended to be exhaustive. People write textbooks on this topics, but we're going to cover the basic approaches that are used in Six Sigma, and the concepts carry over to even more complicated measurement systems than we'll cover. Okay. So again, we'll use the term MSA. And MSA, I'm just going to pick a pen here. So the term MSA means Measurement Systems Analysis, common term. Also, you'll see the term gauge used a lot, even though, and usually it's G-A-G-E, the more common spelling these days. And basically, a gauge is a measurement system. I don't actually like to use the term gauge because when these methods first began, actually in earnest, around World War II, what they were evaluating were typically fairly simple mechanical gauges to measure things. But today we sometimes use gauge to refer to things like analytical equipment in a laboratory, very complicated measurement, say computer-controlled coordinate measurement machines and so forth. So when we say gauge, we're using it in a general term, but as the systems get more complicated, such as laboratory equipment, there are cases where the methods we'll discuss are simply inadequate to fully evaluate those types of more complicated systems. Okay. And when we think about measurement systems, they really fall into two buckets: non-destructive and destructive. Destructive is a measurement that by taking the measurement, you have either destroyed or altered the unit that you're measuring. So the problem is, with a destructive measurement, you cannot measure the unit more than once. An example, if you're measuring the breaking strength of some material, well, you're going to break the sample, and when you break the sample, you can't obviously test it again. So we can't do what we call repeatability. Let me also mention, in these videos, I will not necessarily discuss every slide that's in the set of notes that you have. So you'll notice at the bottom of the slides you can see the page numbers, so you can keep up that way. But there are some material, I'll leave it to you to read, and I'm just going to go forward and talk about, hit the highlights in the notes and discuss the concepts. Okay. So basically, when you do an MSA, two things you're interested in. One, is it accurate? And by accuracy, we mean on average, if you use this measurement system, it will give you the correct measurement. In other words, if I have a tape measure and I measure the length of boards, on average that tape measure will give me the correct length. An inaccurate, or we sometimes say biased measurement system, on average it doesn't give you the correct measurement. So if I'm using a tape measure and it's off by an inch, every board I measure is actually going to be either an inch too long or too short. So if I use the tape measure to decide where to cut the boards are always going to be too long or too short, and the problem is the measurement system was inaccurate. So accuracy is of interest. And then generally we worry about precision or noise in the measurements. In other words, if we take repeated measurements with this measurement system, how much variation do we see among the repeated measurements? Okay. So a measurement system may be accurate, but it could be imprecise, meaning that the measurements are noisy. And just as a general rule of thumb, about 10% of the tolerance range of a part should be, no more than 10% should be taken up by measurement system variation. We'll talk a little bit more about that later. It's somewhat controversial, but it's generally an old general rule that's used in practice. Okay. So on slide 10, I just mentioned 5 general attributes that people talk about with a measurement system. Stability, that is, if I measure the same units or same standards over time, on average, does the measurement system give me the same level of measurement? In other words, is it always on average the same over time, and is the variation the same? An unstable measurement system is one in which the overall average of the measurement system may drift or shift around. We're interested in bias, again also known as accuracy. Repeatability, that's a measure of precision. Repeatability is typically considered the fundamental unit of noise in a measurement. That is, if I measure the same unit under the same conditions repeatedly, how much random variation or noise do I observe? Reproducibility, similarly, is a type of noise, but this is the amount of variation that I see if I take the same units, I measure them repeatedly, but I may actually have different gauges, or I may have different operators measure them. So the total variation I observe over multiple operators or gauges is thought of as reproducibility. So the fundamental measures of precision are repeatability and reproducibility. And then finally there's something called linearity, which very simply is over the operating range of the gauge. If there is bias, is the bias consistent? Okay. So on slide 11, I just want to give you the idea of a measurement system that is not stable. So notice at time period 4, right here, the measurement system shifted. In other words, the mean of the, if you look at the mean of the measurement system has shifted away from the level it was running at. So stability typically most often means that the accuracy of the measurement system is not constant over time. But it can also sometimes mean that the amount of noise in the measurements is changing, but most often it's really a problem of the accuracy changing over time by either shifting or drifting. Analytical equipment in laboratories are notorious for drifting. That is, over time, the overall level of the measurements is trending up or trending down, indicating that you're getting increasingly inaccurate measurements over time. Okay. Again, accuracy or bias simply means if you take a lot of repeated measurements, on average, do those measurements actually coincide with the true value? Okay. Again, you typically measure bias by using standards or references, and you're seeing how close the measurement system comes to matching the true certified or known value. Okay. And then when we talk about repeatability, again, notice that we have the bell-shaped curve or normal distribution. Generally, measurement error or noise in its variation, the patterns of it follow the bell-shaped curve, or as we better know it, the normal distribution. So there typically is an assumption the noise is normally distributed. And repeatability indicates the total distribution of measurements you would get if you repeatedly measured a unit under exactly the same conditions, hence repeatability. So we often think of it as a fundamental measure of precision. So a repeatable system is one in which, upon taking repeated measurements of a unit, you get very little variation among the set of measurements. In other words, this normal distribution would be very, very tight. Okay, so that's repeatability. Repeatability takes into account you may have multiple operators or technicians measure the same parts, or you may have the parts measured on multiple instruments or gauges. This type of variation is referred to as reproducibility. So notice in this case, okay, we have three different operators. Again, notice for each operator, again, we still have our repeatability. In other words, each operator takes repeated measurements of a part. They get the repeatability error or noise. But across all three operators, okay, or across all three instruments or gauges, we get more variability. And essentially, on slide 15, you see a picture of what I'm talking about. So, again, within each operator, there's repeatability variation, and then there's variation between operators, and that all gets lumped together to give you the overall variation in the measurement, sometimes referred to as the gauge error, for want of a better term. So that total variation is what we're interested in, and the total variation is assumed to have two parts. A repeatability part, again, the fundamental noise in the measurements. If you do repeated measurements of a unit under exactly the same condition, how much noise do you get? So you'll notice the repeatability variation is about the same for each operator, but there's quite a bit of spread among the three operators. So the two components, repeatability, reproducibility, combine to produce the total measurement error. Okay, and I wanted to explain something, so I have a little crude drawing here about the idea of accuracy and precision. These two ideas are often conflated by people in talking about measurements, but they're not the same thing. Okay. Again, an accurate measurement means on average you hit the target, the true value. That's accurate. Precise simply says in taking repeated measurements of something, there's a small amount of noise in the measurements. We say the measurements are precise. Okay. So basically, let's look at four simple cases. So the measurement system, by the way, it's either accurate, yes, or it's not. That's very simple. It is or it isn't. Whether or not something's precise is typically a matter of definition by the people doing the study. But let's look at our cases. So here's a case, okay, where we have a measurement system that is accurate and precise. Think of shooting at a target. So again, this is a crude drawing. So I have a bullseye, and notice on average the shots are all right around the target. So we'd say it's accurate and precise. But notice to the right, again, we're accurate on average. Our measurements will hit the target, but notice there's a lot more variation. So we'd say, yes, it's accurate, but it's imprecise. Okay. So an accurate measurement system can suffer from too much noise. It's not precise. Well, what about a system that is not accurate? Well, it can be inaccurate and very precise, meaning you very precisely miss the target. So here we have a bunch of points. They're tightly bunched, but they're off target. Typically in measurement systems, this is actually the reason for calibration. Okay, to try to bring the measurement system back onto target, just like somebody doing competitive shooting or competitive archery would be targeting the bow or the firearm so that it will be accurate. And then finally, there's the worst case of all. You're not accurate, and your measurements are all over the place. By the way, one of the difficulties is if you have a great deal of noise in the measurements, it's very hard to discern accuracy. Okay. So these are basically the four general categories we think of when we think about measurement systems. And the ideal world is it's accurate and it's precise. But the world isn't always kind to us, and measurement systems often are not ideal. Okay. Now I mentioned linearity, and I just want to explain briefly what it means. And that is, over the range of the instrument, look at the vertical axis. This is the range of measurements it's meant to take. And then on the x-axis are the actual measurements. So the solid diagonal black line is where we want all the measurements to fall. That means we have accuracy. But notice the orange line indicates there's an offset. In other words, there's a bias or inaccuracy. In a linear system, the good news is the amount of bias is the same over the whole operating system. So if there's an offset of some amount, the good news is no matter how big the feature of the unit we measure, the offset is the same. In a nonlinear system, the bias is typically proportional to the size of the feature you measure. This is very undesirable, but unfortunately occurs quite frequently in practice. For instance, an instrument that is incorrectly calibrated will typically increase the inaccuracy of the measurements as the size of the feature goes. An example, the measured concentration of some samples, you're measuring for some, say, serum glucose, instruments not properly calibrated, as the level of serum glucose grows, the bias or inaccuracy in the measurements grow with it. We call this a nonlinear system. Okay. We're not going to get really much into linearity in this discussion. It's not typically looked at closely in many Six Sigma studies, but you can assess it. The key is if you want to assess linearity, then you've got to have known standards or references. That is, you need units to measure in which you are confident you know the correct value of them. For instance, in measurement systems, many people buy certified standards from the National Institute of Standards and Technology. A very important business for them, and those standards are certified to have a specific value. So you measure them with your system, you can tell whether or not your system is accurate. Okay. So basically, stability, bias or accuracy, repeatability, reproducibility, and linearity. Stability, basically consistency over time, is really difficult to establish in a measurement system study. Typically, stability requires you to measure known standards with your gauge or your instrument or measurement system over time. So it's not unusual, for instance, in laboratory equipment, they have references or standards, and part of their quality control is to measure those standards periodically to make sure the instrument is stable. That is, the mean response of the instrument is not shifting around. Okay. So basically, we're going to now talk about something called gauge R&R. Okay. Again, gauge is often spelled G-A-G-E, but we use the more formal spelling here. And this is a really old idea. As far as I can tell, the origins of it seem to have been somewhere around World War II, where we were doing high volume manufacturing, and the capability of measurement systems were really starting to be scrutinized and called into question. So engineers started developing ways of evaluating the system. Gauge R&R, unfortunately, makes a couple of assumptions. One, it assumes the gauge or measurement system is stable or consistent over time, and we really cannot evaluate that in a gauge study. Again, you need to measure references or standards repeatedly over time. And gauge R&R assumes the measurement system is unbiased, it's accurate. And in the early context of gauge R&R, where they typically looked at mechanical gauges that are typically made to very precise manufacturing standards, typically you could assume the gauges were unbiased, so nobody really worried about bias. In doing gauge studies, it's a good idea to get references or certified standards and check for bias in advance if it's appropriate for the measurement system. Sometimes it's an assumption you'll just have to make, and there's no way to evaluate bias. Okay. So remember, I talked about breaking down the sources of variability. So at the bottom of slide 22, okay, on the left-hand side is the total measurement. We call that sigma squared measurement, where sigma represents variation or noise. For instance, the sigma in Six Sigma. So sigma squared measurement is a theoretical measure of variation in the measurement system, random variation, and it has two sources, the repeatability variation and the reproducibility variation we talked about earlier. So all the variation, and again I mean random variation or noise, this has nothing to do with accuracy, is broken up into these two components, repeatability and reproducibility. But in recent years, and I say recent, over the last 20, 25 years, they've brought into the mix another potential source of random variation, and this is sometimes called operator by part or unit variation. That is, different operators or technicians measure the units differently. We say there's an interaction of the two. So in a laboratory, some technicians, for instance, might prepare the samples differently, might calibrate differently, so we discover there's a lot of variation based upon how the operators actually measure the different samples or units. So that's a third unit of variation that has become rather popular as I said, in relatively recent years. Okay, so if we're going to do a gauge R&R, what are the steps involved? Well, on slide 25, I'm not going to read them to you, but basically these are your steps. Okay, you pick the units or samples that you're going to use to measure and how many operators or technicians will take part. Okay, pick a representative gauge or measurement system. By the way, gauge R&R, you can either have multiple operators or multiple gauges. You can't have both. This is a fundamental limitation of gauge R&R. Okay. And again, you go back to the origins of gauge R&R, where they're looking at mechanical gauging, okay, where again, these gauges are made with a great deal of precision, so it would not occur to them to worry about two gauges being fundamentally different, so they'd simply pick a gauge. There is nothing to stop you in doing your study to have multiple operators and multiple gauges. It's just not a class part of what we call classical gauge R&R. Then you would design the study, and by the way, I will not cover it, but I have given you a set of notes on how to create a gauge R&R study in the JUMP software. Okay, so let's take a quick look at an example, and this is based upon a real measurement system study. There's a company that makes these important safety valves. I won't get into all the details. And they have a particular component, a fitting that goes onto the valve, and they need to measure the outside diameter of it, and it's actually in an awkward position, so it's difficult to measure. So they've developed a gauge, a special type of gauge, to try to measure this outside diameter. Okay, and for this study, they picked 3 operators and a sample of 5 fittings. And by the way, these are not the actual specs, these are rather loose. The specifications were the target is 60 thousandths plus or minus 30 thousandths. And I can assure you these days, these would be considered enormously wide specifications of that as compared to what most people work to today in manufacturing. Okay, so what I'm going to do at this point is go over to JUMP and take a look at the data and talk through it. Okay, so here's the data. So we have operators, parts, and readings. Those are the measured diameters. So we go to Analyze, Quality and Process, and pick. There's 2 choices, but go ahead and pick Variability / Attribute Gauge Chart. We'll use just one platform. JUMP actually has 2, but I want to be consistent and just use one. Okay. So, first of all, the response is reading. Okay. Where it says grouping. Okay. What are the groupings? Well, the operators are the groupings of the measurements. Notice there's a window where you can put part ID, so that's where we will put part. Okay. So what JUMP will do, it's going to sort out the measurement variation. It's actually also going to sort out the part variation. Remember, I'm not really interested in variation, manufacturing variation in the fittings. I'm interested actually only in the variation in the measurement system. Okay, so I'm going to go ahead and click OK, and then you'll see what's sometimes called a multivary chart. I actually like these charts in general. It's basically a stratified scatter plot. Again, an old term for it going back to the 1930s is a multivary chart. Okay, that's a popular term in Six Sigma. And in the report menu, there's a few things I think are of interest to look at. One, I like to connect the cell means for the visual effect. And I like to look at the group means. So the three group means are the averages for each of the operators. By the way, down the bottom you see the standard deviation chart. This is the standard deviation from each set of two measurements made by each operator on each part. Remember, there are two repeated measurements on each part by each operator, and all operators measured all the same parts. We call this fully crossed. All operators measured all the same parts. Okay. Well, one thing to notice in the plot, first, within each operator, just look at the basic part variation pattern. Okay. Ideally, the pattern should be more or less the same for all the operators. If all the operators are measuring the parts in the same manner, this general pattern that you're looking at should be the same. Notice there is a discrepancy for Neil on part 2. Okay, and that's actually going to show up in our analysis. For some reason, Neil did not seem to measure part 2 the same way as the other two operators. So there may be an operator by part interaction going on. Okay, notice the variation within the replicate measurements. This is repeatability. Okay. And then notice the variation between the operators. Basically, look at the offset in the overall mean measurements. So visually, I see a number of things. One, there's a lot of part variation. Not surprised. I picked the parts to be very different, so I'm not surprised by that. If I look at the means for each of the three operators, they're very close together. In other words, it doesn't look like there's much variation among the three operators, but when I take a look at the variation, the repeatability, I see some, overall there's some fair amount of variation. So how do we quantify this? Well, what we do, we go to the variability chart menu and go down to the near the bottom. It says gauge study and pick gauge R&R. Okay, and it says type of model, that is what has been measured. I said this is fully crossed, which means all operators measured all of the same parts. So we call this crossed, and a typical gauge R&R study is fully crossed. Okay. Now notice there's this multiplier 6. What this stands for is 6 standard deviations. Okay. For a normal distribution, I'll review this in the notes. Okay. Typically, 6 standard deviations covers 99.73%, or almost 100% of the variation. Okay, and my tolerance interval is 60 thousandths wide. Okay, so I just click OK, and I get a report. Okay, and what you see in the report is something called the study variation. In other words, I'm going to go back to the notes and explain this, but study variation is the standard deviation for each of these measured quantities multiplied by 6, and that represents what they would consider the full range of variation you would see in practice. In other words, it covers one normal distribution of measurement noise. So notice repeatability, look carefully, covers 32% of the specification range. So a third of our specification range is taken up with repeatability. Reproducibility, okay, the next one is almost 43%. Okay. And notice a big chunk of that reproducibility is an operator by part interaction. That's primarily driven by the fact that Neil measured part 2 very differently, okay, than the other operators. So altogether, the total measurement variation takes up almost 54% of the specification range. So that means I've got a manufacturing specification of 30 thousandths to 90 thousandths, but 54% of that range is taken up, okay, by the measurement system itself. Remember, generally we like it to be no more than 10%, maybe 30% max. So that's a problem. This is actually not a precise measurement system. And that gauge measurement error is often stated by something called the precision to tolerance ratio. That's the ratio of the total measurement error to the tolerance ratio. So basically this is 32.12 divided by 60, so the measurement error is taking up 54% of the spec range. Okay, so I'm going to go back to the notes and just very quickly summarize what I went over. So we went through a lot of this in jumps, so I'm not going to repeat it. Okay, and here's what I meant by that multiplier of 6. Okay, we assume the measurement error overall follows a normal distribution. In other words, its pattern of variation follows the normal. And for a normal distribution, okay, that's something I didn't want it to do. Okay. Okay, there we go. For a normal distribution, that means 99.73% of the total measurement error is in a window of 6 standard deviations. So that's how we typically define one normal distribution for purposes of measuring gauge capability. Okay. So here is again what we call the study variation. That's the variation, and it says 6 times the standard deviation. Okay. And we see the breakdown. Okay. And the percent of tolerance. By the way, those percent of tolerance numbers don't sum to anything in particular. That's one of the issues I have with the use of that, what's called the study variation, and those percent of tolerances. They have some value. It gives you an idea of how much of the tolerance range a particular component of variation takes up. But the downside is they just don't add to anything in particular.